Hi, I'm Kaushik Roy. I'm a professor of electrical and computer engineering at Purdue University. And today I'll be talking about rethinking computing with neuro-inspired learning. I'll talk about the entire stack going all the way from algorithms, architecture to devices. Deep learning certainly has made a huge amount of progress in the recent past. And if we look at AI is certainly scaling across applications, investment, and people. However, there are several challenges. Now let's look at the compute demand for AI. In particular, if I were to consider network architecture synthesis and on a large transformer as an example, turns out that the number of operations required is about 10 to the 21 or so. That's humongous. And correspondingly, if I were to look at the energy consumption or the estimated CO2 emission from NAS on transformer, that's about 315x higher than air travel from New York to San Francisco per passenger, or about 5x higher than the lifetime of a car. And that's humongous. So on the other hand, let's look at edge intelligence. So we did a case study on object recognition in a smart glass with a state-of-the-art accelerator like Google HTPU. So we implemented RetinaNet for object detection on a smart glass and considered what's the time for the battery to die. It turns out that the time to die for the battery under ideal conditions is of just about an hour. So the question is, where do these inefficiencies come from? So inefficiencies come from not having the right kind of algorithms. These algorithms are not being implemented also in the right kind of hardware architecture. And finally, the devices that we're currently using as CMOS devices, they are really good on-off switches and may not efficiently implement the synaptic and the neuronal functionalities. Now, going beyond the compute demand, there are several inefficiencies that we need to address. Can we learn with less data? Today, the amount of data required for learning is also humongous. Now, what is the generalization behavior of the networks? Are these networks robust? Are they robust to, for example, the adversarial inputs? And finally, are we able to learn in a lifelong manner? So today's networks are really good in learning, task A, task B, task C, all combined together. Is it possible to learn in an incremental fashion without catastrophically forgetting the old tasks? Now, these are very important problems, but today I'm really going to be focusing on the compute demand of AI. Now, to tackle the compute demand of AI, it's hopefully evident that there's a need to really look at the entire design stack, going all the way from learning algorithms, selecting the right kind of network architecture, to where it's going to be implemented, what kind of hardware substrate that we need, and finally to the circuits and devices. So with that in mind, and we also know that brain is quite efficient, can we take cues from the brain? So what are the cues that we can take? What kind of neuron models that we should use, the learning algorithms, the network topology, and the computing principles. Now let's go into a little more details. What kind of neuron model should I use? Should I use, for example, a leaky integrate and fire neuron? Should it be a stochastic neuron? Or should we use, for example, a more generic Hodgkin-Huxley model? On the other hand, if we are to really think about the learning algorithm, should it be a localized learning, as has been observed in the hippocampus of rats, for example, the spike timing dependent plasticity, or should we use a more global learning or a combination of both, like backpropagation is a global learning that has been used in the standard deep learning community a lot. On the other side, what kind of network topology is important? Should there be long-range connections? Should there be feedback connections? And finally, what kind of computing principles are we going to be using? If you're, for example, using spikes for computing, what kind of hardware should I use? Should it be an event-driven asynchronous hardware? Should the memory and the compute be tightly integrated together? Should there be some computation done in the memory itself, as we see in the brain? What kind of input coding should I use? Should it be rate-coded inputs for spikes? Should it be time-based coding? Should it be a direct analog input? Or should I use, for example, devious inputs coming from, let's say, specialized cameras? So with that in mind, let me just talk about the neuron synapses and the learning algorithms. And in particular, as I said, I'll be talking about spike-based algorithms and how some of these algorithms can potentially lead to interesting learning and at the same time energy. So let me get started with the neuron model. To start with, I'm showing a biological neuron, or the spiking neuron with connections, two neurons connected through axons and synapses. Turns out if you have a bunch of input spikes that are coming in, and what happens to the membrane potential of the neuron is that it goes up. And if there are no spikes, there's a decay. But if you have a bunch of spikes that come in beyond a certain point, the membrane potential crosses a threshold and the neuron spikes. Now that can be represented in terms of a leaky integrated fire equation, as I'm showing there. On the other side of it, it's also possible to actually ignore leak and consider integrate and fire neurons. And in this particular case, as you can see, which is shown in red, the membrane potential doesn't have any leak, and hence there are possibly going to be more number of spikes that you get in an integrate and fire kind of neuron. And then finally, let me also quickly discuss stochastic neurons. Stochasticity certainly has been observed in the neurons, and what I'm showing here is a sigmoid neuron with stochastic switching behavior. In other words, based on the input that comes in, turns out this neuron switches with a certain probability, and this can also be considered to be a spiking neuron. Now let's talk about synapses and synaptic updates. In the last slide, I talked about the spiking neurons. And in this case, let me get started with some localized learning called spike timing dependent plasticity. In this particular case, I'm showing an example of 3 input neurons, I1 through I3, and an output neuron O1. So if I take an example where a bunch of input spikes are coming in this particular case from I1 and I3, and if the output neuron spikes, which is shown in red, at a particular time, then by looking at this graph, you possibly can say that, hey, the output neuron was spiking because mainly due to I3, and it also depends on I1. So to that effect, what one can do, and one can do a synaptic update, and based on the timing difference between the output neuron spiking time and the input neuron spiking time. So you can update W3 based on that, and similarly you can also update W1. The W1 update is going to be different from the update for W3. Now these kind of synaptic updates has been observed in the hippocampus of rats by Bu and Pai back in 1998 in their seminal experiments. Now, if I were to really look at what the weight updates it's going to be, the new weights are going to be the old weight plus these delta changes that I'm showing due to the spike timing difference. Now, if I do have now a spike coming in at from I2, which appears after the neuron has spiked, the O1 neuron has spiked, obviously then I2 is not, the spike is not related to the output spike, and hence one can depress the weights. And that's what I'm showing in this particular case. Now one can also use backpropagation for training these spiking neural networks. The only caveat is that some of the gradient calculation that we do are not possible because of using spikes, and hence there's a need for approximations. And I'm not going to go into the details of it, but one can refer to different papers where one can use surrogate gradient based techniques to training of these neural networks. So far, I've talked about the neuron and the synaptic models and different ways of training these spiking neural networks. Now, let's take an example of optical flow estimation, and we're going to be trying to implement optical flow estimation using spiking neural networks. To that effect, we're going to be using event-driven cameras, and these event-driven cameras are actually quite interesting. That the relative motion between an object and the camera would lead to spikes. So if there's no motion between, there's no relative motion, then there wouldn't be any spikes. So these cameras can actually generate spikes as inputs, which can be directly fed into a spiking neural network. And to that effect, what I'm really showing here is for optical flow estimation, an architecture which includes encoder, residual block, and a decoder. I'm not going to be going to the details of this architecture, but what I'm showing here is what's shown in blue is a spiking neural network block. And the later part of the network, as you can see, is an analog neural network. And the reason why we ended up using a hybrid architecture like that is because the input block S and N is very well suited for the spike inputs which are coming in from the event cameras. But on the other side of it, it turns out, and we can train it using the backpropagation technique that we talked about earlier. However, the spikes do die in the later layers, and due to these vanishing spikes, sometimes it's difficult to train the later part of the network. And to that effect, actually, we use an accumulator, which is shown in red, and use that accumulation to actually train a network, the later part of the network, which is actually the standard deep learning or ANN or analog neural network. And we use this architecture actually for optical flow estimation. And I'm showing here is an example of real-time flow prediction, where one of my students is working in front of the camera, and we basically have these input spike images which are coming in, and then I'm also showing the predicted flow output and the mask predicted flow. And as you can see that, and I'm not showing all the results here, it turns out that the implementation of this is quite energy efficient compared to the standard way of doing implementations using a deep neural network. And finally, one of the things that I also would like to mention is that, in fact, the error that we get out of using these spiking neural networks is actually better than, for example, if you were to use the standard ANN blocks. And that's partly because of the fact that we can effectively use the membrane potential to store previous information. Now let's take another example where I'm going to do gesture recognition using the liquid state machines. And these liquid state machines have been trained using the spike timing dependent plasticity based localized learning that I talked about. So I'm not going to go into the details of this network, but these LSMs are actually random networks with the output being actually trained in this particular case using spike timing dependent plasticity. So let's take an example where we actually use the LSM coupled with the DVS camera to fly drones. And here my student is showing the gestures to the drone to go up or down or left or right. And it's processed by the liquid state machine, giving the command to the drone to go up, down, left or right. Now let's change gear a little bit and talk about what are the different kinds of hardware fabrics and the devices that can potentially be used to implement some of these algorithms that I just talked about. Now, one of the most important compute primitives required for deep learning is the matrix vector multiplication unit. So there's a need for really thinking about efficiently implementing such MVM operations. But for the spiking neural networks, you may not require the multiplication. What is required is the accumulate operation. But finally, there's also a need for calculating the membrane potential in such spiking neural networks. Now, these networks are usually implemented in CPUs and GPUs. GPUs certainly can efficiently implement the matrix vector multiplication operations, but they still use actually what's called the von Neumann architecture, where the memory and the compute unit are separate. Now, it turns out there's something called the von Neumann bottleneck, and that's basically the traffic between the memory and the CPU, and that can be quite large and leads to inefficiencies. So to that effect, is it possible to come up with really the circuits and architecture that can efficiently embody the computing principles of the brain? Or in other words, would I be really able to do compute in the memory itself, or compute just very close to the memory, thereby implementing some of these matrix vector multiplication or these accumulate operations right in the memory itself, and be able to alleviate the von Neumann bottleneck. The algorithms that we're looking at, deep learning, are usually error resilient. So it might be possible to use approximate or stochastic hardware, leading to actually energy efficiency. And finally, for spiking neural networks, there's a need to think about event-driven computation and hardware that can support such event-drivenness. Now, at the end of it, some of these are implemented in CMOS technology. And as I mentioned, CMOS is certainly efficient as a switch. However, they may not be efficiently be able to implement neurons and synapses. To that effect, there's a need to really think about new devices, new interconnects that can alleviate the problem of power consumption in deep learning. Now let's consider some of the devices that can efficiently implement the neurons and synapses, or in other words, the neuromimetic devices. So in this slide, I'm showing a bunch of colorful devices going all the way on the left as a ferroelectric transistor to skyrmions, spin valves, to on the right, for example, the magnetic tunnel junctions, SOT-based magnetic tunnel junctions, and RRAMs and PCRAMs. So RRAMs, PCRAMs, and some of these magnetic tunnel junctions are quite mature. And I'm going to try to focus on that and try to see and compare that with the standard CMOS technology. So a few things that are quite important turns out to be, leakage cell area, write energy, read energy, and of course the endurance. And that's what I'm really focusing on in this particular case. Each has its own advantages and disadvantages. If your endurance is low, for example, in case of PCMs and RAMs, they may be there might be difficulty in implementing them for training, but might be suitable for inference only kind of architectures. Now, going forward, how do I use these devices for computations? And in this particular case, I'm just looking at spin transfer torque devices, but they're it's equally important to understand that they can be useful for other kinds of devices such as PCMs and RAMs and so on. So if I were to really think about the weighted summation, which is required of the matrix vector multiplication and the thresholding operation, the weighted summation operation can be implemented in a crossbar array, which ends up doing summation of VI times GI, GI being the conductance, and that can implement, for example, in a crossbar, analog crossbar for doing the matrix vector multiplication. Now, on the other side of it, the thresholding operation can certainly be used using some of these devices like a magnetic tunnel junction or PCMs. Now let's delve a little deeper and try to see how some of these non-volatile memory elements can be used in matrix vector multiplication and finally in a computing architecture. What I'm showing here is a matrix vector multiplication operation, which, as I mentioned in the previous slide, that a bunch of inputs which are coming in, which are V1, V2, V3, which are voltage, and what you get at the output is summation of VI times GI, which is current. Now, each of those elements, which are the non-volatile storage elements, can potentially be, as I mentioned, a PCM or an STT-RAM and so on. Now, finally, each of those devices has to be also associated with an access transistor or a device which is an access device, a selector device. And finally, what you can really do is you can take these computation units, which are these matrix vector multiplication units, and you put a bunch of them together. Output of each of those matrix vector multiplications connected to a neuronal unit, and they can be communicating in an architecture as shown there in an NOC kind of architecture. Now, one thing that turns out to be quite important is when these crossbars are communicating with each other, we'd like them to communicate not in the analog domain, but in the digital domain, and there's a reason for that, so that you can have better noise immunity. For that, there's a need for having analog to digital converters. In other words, you have to connect the output of these crossbars through some current to voltage converters and then to an analog to digital converter. And it turns out that the analog to digital converters do end up taking a good amount of area, and the complexity of those devices can dominate the power consumption of such an architecture. Now, based on the matrix vector multiplication unit that I mentioned in the previous slide, one can potentially think of an architecture where there are a bunch of cores which are shown there, and each of those cores implement those matrix vector multiplication unit using the crossbar. There are a little more logic required to do other kinds of computations, and also some shared memory in each of those tiles as I'm showing here. And each of those tiles now can be connected together using a network on a chip. Now, this turns out to be a massively parallel architecture, amenable to data level parallelism, and can potentially implement highly efficient machine learning inference. The results are actually quite interesting. We actually did compare the results with Skylake, Pascal, with Puma. And again, remember that this is actually an implementation of an ANN and not an SNN, but SNN implementation is going to be very similar. In fact, on top of that, it can potentially give you a little more energy efficiency. But what I'm showing here is under ideal conditions, it's possible to get good amount of improvement, of the order of 100x or so, or in fact, in some cases more in energy efficiency, compared to the standard CMOS way of implementing some of these circuits. So here are some parting thoughts. Bioplausibility in any way is not be all end all. It's a means of achieving, I believe, energy efficiency and new learning. and to in fact achieving robustness. And they do have a potential for edge computing, the spiking neural networks, especially with devious cameras and so on that we have seen. We also looked at the neuromimetic devices, and they can effectively harness the neuron and the synaptic functionalities, and the possibility of getting a large improvement using such devices along with a spatial architecture. And finally, I believe that for these networks, the temporal domain is the key. Are we efficiently using the temporal statistics in the best way to learn? Finally, at the end of it, I believe that algorithm hardware co-design guided by the biological principles can be a pathway for the next generation neural computing. Thank you.